So today we're starting a totally new chapter on rational expressions. The good news is a lot of the stuff that you're going to see in this chapter are things that you would have seen before back in Math 20-1, so it's not going to be super revolutionary or super new. Let's get started. So chapter 9, rational expressions. We will look at the characteristics of rational expressions today, including their general shape, vertical asymptotes, horizontal asymptotes, non-permissible values, or in other words, NPVs, and their domain and their range. Hopefully it won't be too long of a lesson today. Hopefully I'm also not going to eat my words on that one. Let's get going. So recall that a rational number, this is from way back in like Math 8 or Math 9, a rational number is just any number that can be written as a fraction with integer components. So 0.4, for instance, is a rational number because you could write that as 4 over 10, right? There's an integer over an integer. Negative 2.5 also, you could write that as, I suppose you could write that as negative 25 over 10. That could simplify down to negative 5 over 2 as well, however you want to do it. 3 over 4, that one's already written as a fraction, so of course that is a rational number. And 0.3 repeating, because there's a repeating pattern to it, that actually also indicates to us that it's a rational number because it can be written as a fraction. 0.3 repeating would just be 3 over 9, right? So it still is written as a fraction with integer components. So even though that it goes on forever and ever in decimal form, it still is a rational number. Now, a rational expression, which is what we're getting into in this unit, is a similar idea. It's an expression, usually a function, that is written as a fraction. So y equals 5 over x plus 2 and then plus 7. That works just fine. You could write this as a single fraction if you wanted to. You just have to make sure that 7 had a common denominator, so you'd have to times it by x plus 2 over x plus 2 and then stitch them together. But either way, it's just any expression that can be written as a fraction. And generally, another better way of saying this is you can have a polynomial on the top and a polynomial on the bottom. Now, the term rational in math refers to the fact that the expression is a ratio. You might not have known that. I don't think I ever explained that before, of two different parts. So it's not that it's rational as if it's like, you know, thinking clearly or something. No, it's rational because it has to do with a ratio. In Math 20-1, we dealt with rational expressions to represent mathematically complex scenarios where various rates of change were occurring, such as two people working together to paint a fence, right? So in other words, if we said, oh, this person can paint the fence in 3 hours and this person can paint the fence in 4 hours, if they work together, how fast is it gonna get done, right? Rational expressions were used for that. We won't have to worry about that for now. Let's move on. All right, so we're gonna investigate some of the shapes of rational expression graphs. We got two different rational expressions we're gonna test out here. We got f of x equals 2 over x and g of x equals 5 over x. I'm gonna worry about f of x here first. We're gonna complete the table of values and then sketch the graph on this graph here. I'll just do it all in one. So for f of x, if we're going to plug in negative 10, that's going to give us negative 0.2. If we plug in negative 2, that's going to give us negative 1. If we plug in negative 1, that's going to give us negative 2. And then if we plug in negative 0.5, we're going to get negative 4. And then something really weird is going to happen if we plug in 0. 2 divided by 0 is not possible, so we have to say it's NA. Then if we plug in positive 0.5, we're going to get positive 4. Positive 1 is going to give us 2. Positive 2 is going to give us 1. Positive 10 is going to give us 0.2. So if we were to plot these numbers on here, let's just do it real quick. X is negative 10, so we're looking over here. F of x at that point is going to be negative 0.2, so it's going to be like right here-ish. And then negative 2, when x is negative 2, we have negative 1, so we're going to be right here. When x is negative 1, we're going to be at negative 2, so we're here. X is negative 0.5, so we're in this halfway point. We're all the way down at negative 4. And then, of course, we got nothing at 0. So then 0.5, which is over here, we're going to be up at 4. And then at 1, we're going to be at 2. At 2, we're going to be at 1. And at 10, we're going to be at 0.2. So it might not be very clear what the shape of this graph is here because the points are kind of like all disjointed. But just to help you out, it's actually going to look like this. It's going to kind of weasel its way here. I'm going to try my best with this trackpad. It's going to pass through this. It's going to curve this way. And then it's going to curve straight down without actually touching that y-axis. So I'll put some arrows in the end there. It's also not going to, it's also not going to totally touch the x-axis over there either. It's going to do the same thing on this side, of course. If we were to just connect the dots, we can just get this piece going first. And then we have to connect all the way down over here. There we go. And then this one's going to shoot all the way up, going to positive infinity. Not a very straight line that I've drawn there, but hopefully you get the idea. Let's compare this now to g of x. I'll just change pen color so it sticks out a little bit better. We'll do blue. So g of x is 5 over x. If we were to throw those numbers in here, you're going to find that this is negative 0.5. If we divide by negative, divide by negative 2, that's going to be a little bit different. Okay, so dividing by negative 2 in this one, 5 divided by negative 2 is negative 2.5. Divided by negative 1 is going to give us negative 5. Divided by negative 0.5 is going to give us negative 10. Dividing by 0 is still not possible. And then likewise on the other side here, divide by 0.5, it's going to give us positive 10. Divide by 1 is going to give us positive 5. Divide by 2 is going to give us 2.5. And divide by 10 is going to give us 0.5. So we can plug all those numbers in here as well. Remember, at negative 10, we're at negative 0.5. So we're actually a little further down from that one from before. When x is negative 2, we're at negative 2.5. So we're here. When x is negative 1, we're at negative 5. So we're over here. And then when x is negative 0.5, we're at negative 10. So we're way down here. I'll connect those in a second. I'll just finish the rest of these here. 0.5, we're at 10. 1, we're at 5. 2, we're at 2.5. Hold on, 2.5. Yeah, that's right there. And then 10, we're at 0.5. Okay, now I'll connect the dots here. It's clearly going to be further away from our axes than the original graph was. Let's just polish it off. Doesn't clearly look there either because we kind of screwed up the red graph, but that's fine. Not the end of the world. Here we go. So what I want you to think here is when we have a different value on the top, so we got a bigger value here on the top, how did it affect the shape of our graph? What changed on this one? Why is it like further out? Why is it further away from our axes than it was before? Let's see. So from the previous question, what effect does A have on the graph of y equals A over x? So A, of course, was 2 in the first one, and then it was 5 in the next one. Well, if you think of A as we had thought of it back, like in our very first units of the year, really we're just multiplying our fraction by a different number, because on the top it's just like we multiplied it, right? So since we're multiplying our whole fraction by a different number, this is just a vertical stretch. So the bigger the vertical stretch, the further away you are from your x-axis, so the further away you are from that flat horizontal axis, right? So let's look at some characteristics here. In the graph of y equals a over x, a non-permissible value, so a value that's just not going to show up, is going to be wherever we divide by 0. As we saw in the previous question, both cases when x was 0, we had no answer. That's your non-permissible value there. We don't have a solution there. So in other words, when it's just in this form, we can say that it's where x equals 0. So it's where our denominator here is equal to 0. Next part of this says the behavior of y near the NPV. Well, what happens is when you get closer and closer to that NPV, notice your y value gets closer and closer to either negative infinity or positive infinity. So we can say that y goes to plus or minus infinity. Now the next one here is behavior of y as x approaches plus or minus infinity. Well, if we look back at those examples, as x is getting to infinity, or as x is getting to negative infinity, the value of y is converging towards 0. So we can say that y is going towards 0. Now for our domain on this case, once again, just popping back, our domain is our possible x values. Notice we could plug in whatever x we wanted to, except for x is equal to 0. So we can say our domain is x cannot equal 0. As for our range, I'm not even going to pop back this time. As for our range is our possible y values. It's the same idea. It's y cannot equal 0. Next up, the equation of the vertical asymptote. The vertical asymptote, of course, is a vertical line that you cannot touch. Notice this right here would be a vertical line. I'm exaggerating it, of course. A vertical line that you cannot touch. Well, that equation would be at x equals 0. When x is 0, you have a vertical line. So our vertical asymptote would be x equals 0. And the equation of the horizontal asymptote, so a horizontal line that you cannot touch, well, that would be y equals 0. So I'm not even going to draw it. I'm just going to write down y equals 0. Hopefully that makes some sense. Hopefully that's also like the longest part of the entire lesson today. I know I kind of like took forever drawing those graphs, but let's move on. All right, so now let's talk about some translations of rational expressions. So we mentioned before that that a value in this form can serve as a vertical stretch. I want you to recall that translations by h and k occur if we have f of x minus h plus k. So we'd be replacing the x with an x minus h, and then we're adding a k to the outside. And remember, H is your horizontal translation and K is your vertical translation. So I want you to consider the function y equals 3 over x plus 4 plus 5. Complete the table of values and then sketch the graph. I'm just going to throw these values in here. I've already got them calculated off on the side here. So if we throw in these numbers into this equation here, so throw x is -7, -5, -4, and all that into this, you're going to get 4, 2, not applicable, because -4 is going to make that equal to 0. And then you're going to get 8, 6, 5.75. There's a point there, 5.75. And then you're going to get 5.5. And then you're going to get 5.25 at each of those values. Now, if we're going to throw these in here, this is hopefully not going to take too long. -7 is going to give us 4. -5 is going to give us 2. Notice this time is like a lot less predictable. It's not as easy to follow. -4, it's going to be not applicable. I think you probably guess what's going to exist there, but I'm not going to draw it quite yet. -3, we're going to be at 8. +1, we're going to be at 6. And then 0. That was kind of weird how we, oh, sorry, this should be -1. My mistake. I totally missed that when I was drawing that. I was thinking, why are we going from there to there? I didn't even catch that earlier. That was -1. So when -1 is plugged in here, you get 6. Sorry about that, guys. Anyway, let me erase that. -1, 6, there we go. 0, 5.75. 2, we've got 5.5. And 8, we've got 5.25. So right there. If we're going to join all these together, this one up top is probably a little clearer. I'm not going to like mess around on this one. You can see that at -4 we have a non-applicable. That's where your denominator is equal to 0. Remember from before, that means that you have a vertical asymptote there. So I'm going to make my life way easier. I'm going to draw a vertical dotted line because I know that's a vertical line that my graph is just not going to be allowed to touch. There we go. Now I can see, remember, we're going to be approaching the vertical asymptote. So we're going to come this way and then down this way through all those points. And then on this side, it's going to be the same idea. Notice what this horizontal asymptote is going to be looking like here. It's looking like in our horizontal direction here, we're approaching 5. So I'm actually going to put my horizontal line there and get that in. And I'll actually explain how you can find that in just a second. Anyway, so we'll just combine all this together. It's going to look, it's going to look something like this. Oh my goodness, that is awful. Let me try it again. It's going to look like that. That's better. And down. Awesome. Okay, horrible. I know, like it's not exactly the easiest thing, but hopefully you can follow along with this. If you don't have printed notes, I guess you can't exactly jot these down, but at least understand what the process is here. Let's move on. If we're going to do the characteristics of this one, the non-permissible value in this case is going to be x cannot equal -4, because if x was equal to -4, you'd be dividing by 0. Now the behavior of y near that NPV, it's just like before. Y is going to be going to plus or minus infinity. Now the behavior of y as x approaches positive or negative infinity, on the other hand, so if we go back and look, as x is getting bigger and bigger and bigger and heading this way, or as x is getting smaller and smaller and smaller and heading this way, the behavior of your y value is it's going to be approaching 5. So y is going to be approaching 5. Our domain, of course, is going to be x cannot equal -4. Our range is y cannot equal +5. The equation of our vertical asymptote is going to be x equals -4. The equation of our horizontal asymptote will be y equals 5. And then our x-intercept, that one's going to be a little bit weirder here. Let's just go back. Our x-intercept, of course, is just going to be where y is equal to 0. In order to solve that, you'd have a little bit of work to do. You'd have to go 0 equals 3 over x plus 4 plus 5. Then you'd minus 5 on both sides, so -5 equals 3 over x plus 4. Times by x plus 4 on both sides, you have -5x minus 20 equals 3. Then you have -5x equals, add 20 on both sides, you have 23. And that means x equals, 23 divided by -5 is -4.6. So your x-intercept is x equals -4.6. And then your y-intercept is just wherever x is equal to 0. We already had that in our table. It's 5.75. So y equals 5.75. Hopefully you understand it. This is kind of redundant. We're going to move on to something a little bit better and beefier in a second here. All right, so quick summary. Before we move on to the real stuff today, let's summarize the values of x that would make the denominator of your rational expression equal to 0 are known as your non-permissible values. Okay, so in other words, wherever your denominator is equal to 0, those are non-permissible values. You're not allowed to have them. The NPVs are the only parts of the expression excluded from your domain. So once you have your NPVs, you also know what is not in your domain. Now, when x is equal to an NPV, you have a vertical asymptote where the y values spike towards plus or minus infinity. That's what we're seeing in this graph right here. It looks like it's as it's approaching 4. We have a vertical asymptote that our graph just cannot touch. Kind of went off base there. There we go, that's a little better. So when you have it in the form y equals a over x minus h plus k, your horizontal asymptote will appear at y equals k. This is actually the only way in rational expressions to predict a horizontal asymptote. You have to have it in this form where you have a constant on the outside. And once you have a constant on the outside of your rational expression, that tells you what your horizontal asymptote will be. So that's important to know as well. And this is because the horizontal asymptotes occur as x approaches plus or minus infinity. Remember, so as you're going closer and closer to infinity, in your x direction, of course, that is, that's what your graph's approaching. So in this one, it looks like it's approaching 1 as x approaches infinity. So when x approaches infinity, when you have it in this form, if x is getting really, really big, it's like you're going a divided by some gigantic number. No matter what h is, you're not going to be able to subtract any reasonable amount of h away from infinity. So you're going to be taking a and you're going to be chopping it into an infinite number of pieces. So a is going to get pretty close, or sorry, this section right here is going to get pretty close to 0. So that just leaves your k, right? That's what I'm getting at. Now your horizontal asymptote is also the only part of your expression excluded from your range. So just make sure you understand that one as well. All right, now moving on to true rational expressions. So the rational expressions we've looked at thus far have been pretty cut down. There's only been like a coefficient on the top. There hasn't been any variables. So most rational expressions that we're going to deal with, however, have variables in the numerator as well, like this guy right here, y equals 4x plus 2 over x minus 1. Now, rational expressions in this form are perfectly acceptable to work with for reasons we'll investigate at a later time. We'll deal with it another time here. Don't worry about it for now. But however, the one weakness behind this form is that your horizontal asymptote becomes difficult to determine. I can't tell by looking at this just how it is right now what the horizontal asymptote will be. Your vertical asymptote is going to be the stuff that appears in the bottom. That's no problem. Your horizontal asymptote, on the other hand, you can't determine. You need it in this form to find your horizontal asymptote because then you know your k value is your horizontal asymptote. So this form that we have here, the one we've been working with all day, a over x minus h plus k, we can call this asymptote form. I actually have no idea if it has a proper name. I'm just going to call it that because that's a good name for it. You could also call it like translation form, I guess. I don't know, whatever. I don't even know if it has a name. Let's move on. So changing to asymptote form, that's the big question here. If we have this and we're saying, hey, without throwing in our graphing calculator, how can we find our horizontal asymptote without doing that horrible annoying thing where I make a table of values and plug it in one at a time and it's super, super annoying and super redundant? How can we find that? Well, to turn that into that form, we need to be able to get only a coefficient in the numerator. This means we'll need to somehow write that numerator in terms of the denominator, x minus 1, so we can factor it out. This is a really weird little trick. And it also involves looking at what your coefficient is on your x on the top to match it with what it is on the bottom. On the bottom, we have an x minus 1. It'd be nice if we could get an x minus 1 in here, or at least some multiple of that. Here's how we're going to do it. Since 4x is here, we need to know that we have to have a 4 times an x minus 1. Well, think of it this way. We could write this as y equals 4, and then I'll write it as x minus 1 plus 2 over x minus 1. Now, just changing this, however, has kind of like messed up the whole thing, okay? Because this is not the same thing as what we had up here, but we can make it the same thing because I want you to think of it this way. So just hold on to this for now. If we were to multiply that 4 through, you'd see we'd have y equals 4x minus 4 plus 2 over x minus 1. This is not the same thing as what we started with, right? We had 4x plus 2 on the top. How do we just get a minus 4 in here? That's not the same thing. Well, we can make it the same thing. We have a minus 4 in here now. We can balance out this numerator by just adding 4 as well. When we add 4 after we've minused 4, these two pieces will cancel each other out and we're just left with the normal 4x plus 2 that we had before. But this 4x minus 4 is going to be very useful for us. Let me show you what I mean. So just ignore this for now. Let's use this one now. We can now factor a 4 out of here. So we'll write this as y equals 4 times x minus 1 plus 2 plus 4, might as well just write that as 6, all over x minus 1. Now, fractions can be split into two different pieces. Think of it this way. If you had y equals, let's say, 2 plus 3 over 5, you could say that that's 2/5 plus 3/5, right? So as long as you just split this into two different things with the same denominator, it can still work. We can do the same thing here. We can split this into y equals 4x minus 1 over x minus 1 plus 6 over x minus 1. Then what I want you to notice is on this piece right here, the x minus 1s can cancel. Boom, boom. And what we're left with is y equals 6 over x minus 1. I'll just write that piece first, and then plus the 4 that we had left over. See how now it's in that form where it's a over x minus h plus k? Once it's in this form now, and believe me, this is the exact same thing as what we started with. Now that it's in this form, we can see that we have our horizontal asymptote equal to 4, right? So right there, that is our horizontal asymptote. Hopefully that makes sense. Just to explain it one more time, what I did was I want to make sure that I can get an x minus 1 in the top. So what I often do is I just force it in there right next to the 4, because again, there's nothing we can do about that 4. So I just change the x to an x minus 1. And then when I multiply it through, I got to say, okay, well, what do I need to counteract this? Well, in order to counteract the minus 4 after I bounce that through, we would just have to add a 4. Okay, so that's a way of doing it. All right, so now that it's in asymptote form, determine the following characteristics. So again, I'll just rewrite it here. It was y equals, what was it? 6 over, oops, there we go, 6 over x minus 1, there you go. 6 over x minus 1 plus 4. So now that it's in this form right here, maybe it's going to be a little bit easier, who knows. Non-permissible value, that's as easy as it was in the first place. That's just going to be x cannot equal wherever this is going to be 0. Well, that's going to be 0 if x was equal to 1, so we have to say x is not equal to 1. The behavior of y as we approach that NPV, well, y is going to go towards plus or minus infinity, because again, that's what happens when you go towards your vertical asymptote. That it's just going to go to positive or negative infinity. It's going to go up and down, right? Now, the behavior of y as x approaches plus or minus infinity, that's telling you where is it going, like where's the horizontal asymptote is basically what it's saying. That's where this form came in, right? So as y approaches, the behavior of y as x approaches plus or minus infinity, well, that means y is going to be approaching 4 in that case. Now for our domain, remember our domain is just everything except for our NPV, so x cannot equal 1. It's basically the same thing as your NPV there. As for your range, y cannot equal your horizontal asymptote, so y cannot equal 4. Your equation of your vertical asymptote is x is equal to 1, and your equation of your horizontal asymptote is y is equal to 4. Kind of a weird day today, but that's how it goes. Not gonna lie, you're really gonna want to do these questions. Like, you will absolutely want to give these a try. This is the very beginning of this rational expressions chapter here. So make sure you're giving these questions a try. Page 442, questions 1, 3, 5, 7, 8, and 10. It looks like a lot. Once you get to it, though, it's not too bad. And I don't have to eat my words. We're not too bad today. We're only 23 minutes and something. Anyway, if you need any help, you know how to contact me. Best of luck, guys.